The final application of the determinant that I want to talk about is the cross product of two vectors. I'll admit that in our course, we don't really depend much on the cross product. We also don't depend on really any of the applications that we did today. We could solve all of those problems in alternate ways. But my hope is that you will need these things, that you could use these things in other courses perhaps, and just general understanding of what the determinant can give us beyond just a number that tells us whether a matrix is invertible or not, because that's not very revealing, I'll admit it. The cross product, on the other hand, is quite useful if you take multivariate calculus. So for all of you who might end up taking multivariate calculus, I do want to introduce the cross product. For those of you who are maybe even feeling a little frustrated, this is the fourth video for the day, a lot of teaching. Keep in mind that at the end of the day, you will have all of the formulas available during the exams. So just try to understand what the cross product gives us. So the cross product, let's start with the definition. The cross product of two vectors u with components u1, u2, u3, and v with components v1, v2, v3 is a vector. So remember, the dot product was a number, just a scalar. The cross product of two vectors is a vector, and it is given in the simplest way using determinants, although that's sort of abusive notation. So it's defined in this way. In the first row, you have I, J, K. What are I, J, K? So this is a bit of physics notation, really. I, J, K are the three columns of the identity matrix. So the direction along the x-axis, along the y-axis, along the z-axis. I'll write those. And then you put the two vectors in the second and the third row. So here is u1, u2, u3, v1, v2, v3. Now here we always, we use determinants here to describe the formula. All of this is not truly valid, because when you write the determinant of a matrix, you need to have numbers or scalars as the components of the matrix. But here, the first row is actually a whole matrix. These are vectors. Vector, vector, vector. So the vector I, also in calculus, sometimes it's written with a hat. The vector I is just 1, 0, 0. The vector j is 0, 1, 0. And the vector k is 0, 0, 1. So the three columns of the identity matrix. We will do expansion along the first row here to compute this determinant. And by doing that, what we're going to get is the determinant of the first minor. So we have u2, u3, v2, v3 times the vector I. So the number that we get from the determinant sort of goes into the first component of the answer. Then remember, j comes with a minus because it's in the position 1, 2. So minus the determinant that we would get by removing the second column in the first row. So we have u1, u3, v1, v3 times j plus u1, u2, v1, v2 times k. So how do I get this matrix? I remove the row and column where k is located, and I get that minor. Now, what this means, you see, this is just a number. The determinant of a matrix is just a number. This is just a number. This is just a number. Now, I has a 1 in the first component, j has a 1 in the second component, and k has a 1 in the third component. So in the end, you get this vector, okay, where the first component of the vector is the first determinant. So that's u2, v3 minus u3 v2. Then you get the second determinant with that minus sign. So I'm going to switch places here. I'm going to write u3 v1 minus u1 v3 because of the minus, things get flipped. And then I get u1 v2 minus u2 v1. So this is that cross product. This is u cross v. You see that it is a vector. Now this vector has some very interesting properties. The most important one, in my opinion, is that this vector is orthogonal to both u and v. So u cross v, this is a vector, let's call it w, is orthogonal to both u and v. So imagine this, you have a vector u, you have a vector v. By the way, I failed to mention one thing. The cross product is only defined for vectors in R3. So the vectors u and v must be in R3. It's not defined for R2, it's not defined for R4. It only works in R3. Okay, so this is something special for vectors with 3 components. And their subsets, they're inside R3. So when I take 2 vectors u and v, right, if these vectors are parallel, then u and v will, the 2 vectors are multiples of each other, I get the determinant is 0. So I don't even have to worry about anything else, I get the 0 vector. But if the 2 vectors are not parallel, if they come at different angles, note that they actually define an entire plane where they lie, right? This cross product w is actually a vector that is orthogonal to both. It could point upward or it could point downward. We don't know. It depends on how we've taken u and v. And I'll tell you what that choice needs to be. This vector w is orthogonal to both v and u, which means that it is orthogonal to the entire plane where u and v are. Now, one point on the plane and a vector perpendicular to that plane or orthogonal to that plane defines everything in calculus. So if you take this in calculus and you understand how orthogonality works and how vectors work, things will be a lot easier for you. So those who intend to take multivariate calculus, pay attention to this video. It is very useful. So when you take the cross product of 2 vectors, what you get is another vector which is orthogonal to both u and v. Let's demonstrate that that's really so. In fact, it's not quite difficult. What was orthogonality? If you all recall, orthogonality means that the dot product of u with w or the dot product of v with w is 0. So that's the first property that I want to show, that u is orthogonal to u cross v, and that v is orthogonal to u cross v. If we can show one of them, we've actually shown the other one by a very simple manipulation, which perhaps should have been rule 1. Now, we have a formula for u cross v. It's right here. So I'll copy that formula for u cross v. Of course, if you remember this interpretation, then computing the numbers here is nothing difficult. You all know how to do it if you can handle determinants. So my formula for u cross v is right here. So this is u cross v. I get a vector. And to show orthogonality, I need to show that the dot product of u with u cross v is 0, right? Those are equivalent statements. So then let's take the dot product. U transpose times u cross v equals, so remember that's u1 times u2 v3 minus u3 v2. So u1 times the first component of u cross v plus u2 times the second component, which is u3 v1 minus u1 v3 plus u3 times u1 v2 minus u2 v1. Now all you have to do is sort of open parentheses and see that that is really, that things cancel out. So I'll use different colors here. We have u1, u2, v3, and now I need it with a negative. So u1, u2, v3. Where is v3? Here's v3, u1 and u2, and I have a minus sign. So actually this cancels out with this. Then I need u1, u3, v2 with a plus sign. So u1, u3, u1, u3, v2 with a plus sign. So you see this cancels out with that. And the other two cancel out as well. So you have u2, u3, v1, u3, u2, v1 with a minus sign. So this cancels out with this, and indeed we get a 0. And you can check that if you replace the letter u with the letter v, you're going to get zeros as well, because you have these pairs. You have u2, v3, u3, v2. So you see uv, uv, the indices change places. Well, you also have u2, v3 in another, well, you will have u2, v3 just because you're multiplying by the u's. But always here, u and v change places and they change indices. U and v change places and indices. So when you multiply by v, you're going to get a 0 as well. So the cross product is a vector that is orthogonal to two vectors. So let's say, how can we use it in the context of problems that we've already been solving? Let's say I give you two vectors that lie on a plane and I say find me all vectors, or describe the space of all vectors orthogonal to these two vectors that I have in a 3D plane. Literally, you can just take the cross product and you've solved the problem. All vectors that are orthogonal to the vectors uv must be multiples of the cross product. So there is one simple application. Another property of the cross product, which comes directly from determinants, is that v cross u is minus u cross v. Why is that the case? Because if you recall, the way u cross v is defined is ijk, and then I have u as a second row, v as a third row. Whereas in v cross u, I have ijk, then v as a second row, u as a third row. Well, a row exchange changes the sign, so that's where minus comes from. A row exchange, or switching uv, changing places of u and v means a row exchange, and that row exchange implies change in sign. The cross product has a few other properties. So another property that's easy to see from determinants is that the cross product of any vector with itself is 0. So that means u cross u is 0. How do we see that? Just from the definition. U cross u, if it is interpreted as a determinant, then you have u in the second row and u in the third row. Well, you see that you have two equal rows. The determinant must be 0. Of course, I can generalize this and put a constant here so that the two rows are multiples of each other. Again, you have the determinant being equal to 0. That says that the cross product of two parallel vectors is the 0 vector. We also have one more property to say about the cross product, which I will write and maybe end it there. The cross product is a vector with length u times v times the sine of the angle between the absolute value of the sine of the angle between the vectors u and v. So this would be theta. So you can represent it as a vector that has this property, and instead of looking at the components, you can represent it as vectors. Anything else I want to say here? Oh, I wanted to say something about whether the cross product looks up or looks down, right? So here I said you could have the cross product W being upward, or you could have it being downward. Well, as long as you place the vectors u, v in a counterclockwise direction or a right-hand rule, then W will point upwards. So you have to start with u and then go to v in a counterclockwise direction in the way in which you write u cross v. So u cross v. If you go in the clockwise direction v cross u, then your vector W, or the cross product, will be pointing downwards. And as noted, if you switch places between u and v, you change the sign, and that just means you change the direction of the vector W. It continues to be orthogonal, it continues to have the same magnitude, but it is now pointing in the opposite direction. And I think I will, well, I want to say one more thing. And I sort of hinted to that when we looked at the property of orthogonality. So I want to just tie us back to volumes. Triple product equals the determinant of a matrix, which equals a volume. So the triple product that I'm talking about is u cross v dotted with some w. This w is not u cross v that I had before. These are three different vectors. And now the interesting thing, and you can take time to compute what this is, but really what you get is this matrix W1, W2, W3, U1, U2, U3, V1, V2, V3, which is also equal to, if you want to shift W to be at the bottom and U and V at the top, so you could also write it as U1, U2, U3, V1, V2, V3, W1, W2, W3. Let's just look at why that's the case. So if you take this cross product, remember that you get a vector, right, with three components. When you take the dot product, W1 will multiply the first component, W2 will multiply the second component, W3 will multiply the third component. But what are these three components? They're actually cofactors. They're cofactors of this matrix for here, here, and here. So in fact, this dot product is exactly this matrix, with W1, W2, W3 being in the top position, replacing I, J, and K. That being said, I mean, I could also take W on the left-hand side. That's not important because the dot product is commutative. And now, how do I get this equality? Well, to put U1, U2, U3 in the first position, I will first switch these two rows, which will change the sign to minus. But then to move V1, V2, V3 in the second position, I will have another row exchange. So to get from here to here, I actually take two row exchanges, which means that I change the determinant twice, or rather the determinant stays unchanged. Well, this over here is the volume of a box with edges given by these three vectors. Now, what happens when do you get this determinant to actually be equal to 0? Well, you get u cross v dotted with w is 0, so the determinant, or the volume, this is volume of a box with edges U, V, and W. You could get a negative number depending on whether you took U, V, W in a counterclockwise direction or not. But if you just want the volume of a box without care for directions, then just take the absolute value and don't worry about directions or the negative signs. Now the volume will be 0 exactly when the three vectors lie in the same plane. So exactly when U, V, and W lie in the same plane. So you see, we can use this triple product over here also to check for linear independence. If I give you three vectors and I ask you whether or not they're linearly independent, well, three vectors in 3 space are linearly independent if they span the whole space. They cannot span the whole space if they lie on the same plane. So one way to check linear independence of 3 vectors is to check whether or not the box obtained by their edges, or where U, V, W represent edges of the box, has a volume or not. It makes sense that a two-dimensional object, which you would get if all vectors are in a plane, has a volume equal to 0. So you have that squashing happening. All right, that is more than enough for today.